Okay. Hello, everyone. Welcome to another pandemic Learning Glass special. So, here is our topic of today. It's having to do with physics on the microscopic scale of atoms and molecules. So, back in the classical times of when we were trying to figure out how we can apply Newton's mechanics into smaller and smaller scales, before Einstein and that next generation were able to go even into more details of even more crazy things, it's not dissociation, of how these atoms and molecules, first they had to determine whether or not atoms and molecules existed. Einstein and his generation finally settled that debate. So before that happened, there were still some people thinking of different theories, and one of them that was crazy at the time but ended up being correct was the fact that there are atoms and molecules that make up gases, that make up solids, that make up liquids. And on top of that, they can explain how gases behaved. One of the theories postulated was that it's based on the speed of these atoms and molecules, which you can relate to energy. And that was all being formulated. And then that eventually became helped to build a foundation for the ideal gas law, which is used to describe a bunch of other things, like in what we're talking about in class is how do you make semiconductor technology? Well, you make semiconductor technology by depositing by diffusion onto a wafer slowly. How do you control that? You have to know how these particles collide, how these molecules collide. How do you know how these molecules collide? You look at their diffusion behavior or their Brownian motion. How do you start from the Brownian motion? Maxwell and Boltzmann, they helped us postulate some theories that in a gas, these molecules are bouncing off of each other constantly. That was a big stepping stone in the evolution of this theory, that A, there are atoms and molecules, B, that in the gas, they do exist, and they're always colliding with each other, and that is confirms these classical things that we may have learned in physics and chemistry, that there's a proportion of the amount of the gas to the pressure, there's a proportion of the amount of the gas to the volume, proportion of the amount of the gas to the temperature. Putting those together, that became the ideal gas law. And the root of all of that is where Maxwell and Boltzmann had this theory that gases are always moving around and colliding. And then they put a lot of details on that. So who am I talking about? I'm talking about James Clerk Maxwell, one of these huge giants of intellectual physics and engineering that pretty much advanced our technology in leaps and bounds. So this is the literal guy who loved it at the end, but we hated it when we were trying to learn it. This is the person who developed Maxwell's equations. And what they did was they unified the theory and the theory of the transport between electricity, so electrical circuits. We know that that's coupled to the magnetic fields, and it also extends to the same behavior for light. So those equations elegantly captured the behavior of those things that all share the same behavior. Maxwell equation, the same guy. But what's even more amazing, he also, so this is the founder of the electrical engineering. He's attributed with founding the physics behind this, which enabled electrical engineering through Maxwell equations. Then he also developed another field, because some of us go into electrical engineering. I went through thermal fluids engineering. He also developed that as well by using kinetic theory, which we'll talk about. So just by his pure intellectual investigations and abilities as a scientist to figure this out and just out of nowhere develop this theory, not out of nowhere, but building little by little from what existed then, he was able to make leaps and bounds, which ended up to be correct. A lot of his theories were not correct, but what he did was he proposed from the existing kinetic theory, which means that there is atoms and molecules, and they're always bouncing around at a certain energy. What is that energy? It's related to the speed, kinetic energy. And what is that speed? That's what he developed. So what he proposed was that there's a distribution, meaning a shape that you can put an equation on of gases, and then of gas, atoms and molecules, and then it's the idealized basis for statistical mechanics, which is a huge stepping stone towards modern physics. Statistical mechanics, chemical kinetics, because there are atoms and molecules. Chemistry is about how those atoms and molecules change when they're reacting. So before they can react, they have to collide with each other. They have to encounter each other. So they have to encounter each other, they have to collide. So the rate at which they collide is based on this velocity distribution we're going to talk about. And transport, which is viscosity. He also developed the physics and theories of viscosity, which is a way of momentum transport. So this is all based on collision theory. So he did both. He developed thermal fluids in chemistry. He developed electrical engineering and other things. And then another guy, Boltzmann, Ludwig, he went on to further develop this idea of this distribution of energy. So he refined the statistical mechanics which is, what did I say there? Oh, first modern physics. He refined statistical mechanics, which is considered to be the first step in modern physics, going away from Newtonian mechanics, which is still important, but if we want to go to the next level, we need some other ways of thinking. Statistical mechanics was one of those, and I'll talk a little bit about that. And which is one way to think about this was he was correct in his definition of entropy, which is a super important cornerstone of the constraints that Mother Nature puts on us in engineering designs and natural behavior. So he was able to show that this equation holds, which we're not going to talk about it, but this is entropy, and S is entropy, And what he was saying is you have to tie entropy into some statistical analysis of your system in terms of the states and probabilities that your system is limited by. So that you can quantify entropy by these microstates statistics. That's what's in here. And what is that proportion? It's this so-called Boltzmann's constant. So that was where this constant, one of the first appearances of this constant, but as we're going to see, it appears in a lot of other places because it is so important to the underpinnings of all of this physical behavior. Then he used, so I'll put it here, KB, Boltzmann's constant, Boltzmann's constant. It's in the units of entropy, joules per Kelvin. And then he refined Maxwell's energy distribution to make it what it is today, and more refined and formal arguments. So these two help to establish our Maxwell-Boltzmann distribution theory. So the first assumptions that they had was that the first big assumptions at the time, this was controversial, that atoms and or molecules are, that they are flying in the gas, that they are the gas, that the gas is atoms and molecules flying around and colliding constantly. That was the first whole premise of this whole analysis. A, that atoms and molecules are the basis of the mass. They're the point contacts of this, what this mass is. Like this whole concept of gas is that there's these localized concentrations of mass called atoms and molecules that are flying around and colliding. That was not a fully agreed upon starting point for the science community at that time. And then you can attribute the energy can be attributed to these particles assigned kinetic energy. That just from their motion, they're storing their energy. So the faster they move, the more energy they have. And they tied it to temperature. That was one of the other big leaps. That the system that they're looking at, this pocket of gas, is at thermal at some temperature that you can define as, just T, some temperature. Okay. So there's a few other assumptions, but that's it. That the controversial ones was that all of this action, all of this behavior that we're seeing in terms of how pressure is proportional to temperature, how volume depends on the number of the mass of the gas you have, all of these measurements were done similar times, and these theories, these observations were getting tied to different theories. A lot of them were wrong, but this Maxwell-Boltzmann distribution turned out to be the best summary of what's going on. So it's saying that, according to Maxwell-Boltzmann, they said that that atoms and molecules exist, and they are part of this not dense gas. It's mostly empty space, and it's particles flying around. And when these particles fly around in empty space, they collide every now and again. And the details of that also is that that there's no other energy interaction besides just an elastic collision. When they collide each other, they just bounce off and they conserve their momentum. They conserve their energy according to transferring energy between each other if there's a difference in energy. But there's no interaction, and there's no loss in energy and all that stuff. Okay, so let's see. So under these assumptions, the whole application of this theory is that what they said was, let's apply some statistical analysis of this, meaning that there's a distribution, saying that if there is these atoms and molecules flying around, because of the speed that they're going at, we're going to consider that the only energy, there's no potential energy, there's no interactions, it's only going to be interactions in terms of collisions, and that involves momentum transfer according to kinetic energy. So what they said was that there's going to be a probability, an energy probability distribution. So this is a huge leap as well to say that, okay, we don't know exactly what's going on, but we can try to understand it by saying that we know that if there is atoms and molecules, they have to be moving around. They're either going to be have no velocity or an infinite velocity. And I mean, not either or, it's somewhere in between there. That it's going to be anywhere in between there. So when you do that, you can say that, okay, the probability of being 0 or anywhere to infinity, it has to have that range of possibilities. So what you can say is that, okay, it has to be somewhere in there. So this would be the number of atoms and molecules of one specific energy level to all of them in your system. That's the probability. It has to be one of these out of all the other possibilities. And they assigned a shape to this. They said, let's postulate that this is some function, some exponential function with this specific shape. It looks like some energy level over the with some constant, Boltzmann constant. It turned out to be in this ratio of energy to temperature. So that's where the definition, this is all pretty much defining what the definition of temperature is. They're relating it to kinetic energy. They're saying that the temperature is the coefficient tying back to energy of these molecules. That makes sense because the greater the energy, the higher the temperature. That was one of their basic assumptions, and they tied it to kinetic energy. Then, of course, this would be all of them. If you're going to say, what is the energy of the whole system? You just add up each energy level of the rest of the molecules. So this would be the rest of them. You just add up all of the other energy levels. So if we were to plot this, so we would plot this so in terms of speed, the classical whole thing was that this is kinetic energy, so let's tie it to speed. So this would be like 1,000, a typical values that it turned out to be meters per second, super fast. For, let's say, argon gas, this is what the result was. That argon gas, if you were to look at the speed of argon gas, the probabilities at room temperature at 300 Kelvin would be that the energy is certain maxed out. So the area under this curve, it has to be either for somewhere about 1,000 or 0. And the max, according to this theory, happens to be at 400 meters per second for argon gas. So their whole theory was that depending on the temperature, the energy can be tied to speed at this speed of this molecule, and it takes on this shape. So this is the energy level of a molecule. This is all atom molecule energies. Or this is the number, I'm sorry. Number at I. Number at energy level I. The number of all energy levels. So, what is typically done is that you tie these energy levels to momentum, because momentum is part of this theory of quantum mechanics. So kinetic energy and momentum are both useful in this discussion of how you were to connect these behavior of these atoms and molecules, because when you have moving forward in the future, eventually they tie this to the behavior of atoms and molecules in themselves and the electrons surrounding these atoms and molecules. So what they said was that an atom and molecules has electrons orbiting the core, and that orbit of the atoms and molecules has an angular momentum as a way to quantify their energy. So they tied it to the translational momentum to say that, there's a translational momentum, and internally they have these other momentum sources. So we're going to connect that the kinetic energy in terms of momentum it's just using the definition of momentum, P equals mv. So the energy This is momentum. This is the molar mass. So depending on which atom or molecule you're talking about, it has a different mass. So if you break that down into its components, it's the x momentum, y momentum, and z momentum over 2m. So what we do here is we're going to use this whole concept that it has to be to anywhere between 0 and infinity. The way that the statistical distribution works is you don't see it, but there is some finite probability it goes to infinity, and if you integrate all of that, it'll give you the area under this curve, and it should be 1 for a normalized thing. So the next step would be, okay, how do we normalize this? So this here is actually the one molecule partition function for momentum. Meaning that this is the momentum contribution to the momentum energy, translational momentum energy. This partition function ties into another theory, this whole statistical mechanics framework. I'm bringing it here because it's just convenient to not keep writing this. So we're going to call this Q translational momentum partition function equals this whole thing. So again, this is tying energy to temperature, and put this label, call it this whole lump thing Q translational. It happens to tie into statistical mechanics, but we don't have to focus on that. But what we are going to focus on is the fact that at the end, what this distribution does for us, it allows us to have a physical basis to describe what is the relationship between temperature and energy. That's the starting point. This is it. This is the relationship between temperature and energy. And then how do we get the ideal gas equation? How does that relate to the temperature and the pressure, the temperature and the volume, the temperature and the number of moles, and so forth? It's all based on this connection here. Okay, so we can rewrite this probability distribution as so if we want to normalize this equation, well, first express it in terms of this momentum. The momentum of one So if we were to normalize this, meaning that normalize so that the integral over all dimensions of in order to make sure that this is all 100% probability in there, you would have to find some normalization constants. So that means that the normalization constant C equals this transitory translational up, down, left, right partition function divided by 2 So if you're to plug in this integral and you wanted to get it equal to 1, you would have to take this ratio here. So when you do that, that allows you to define a normalized distribution probability function for momentum, to convert this to momentum and normalize it. So you would find a normalized momentum distribution probability function. That would be some function of P of momentum in the X, momentum in the Y, momentum in the Z, equal to I'm missing a pi here. I don't know. Okay. So if you use this definition here to convert to velocity, so the reason why we went to our momentum, because it ties in with this quantum mechanics and statistical mechanics translational partition function. It's the energy, like the way you would consider the degrees of freedom of left, right, up, and down, and then tied in with the atoms and molecules themselves. So let's go back to the velocity. So convert back to velocity. That would be using this definition here, where dp dv you would get the new function in terms of Vx, Vy, there's an M there. Converts to velocity. And then the end result is tying it to the scalar amount. So from velocity to speed. So for speed, the magnitude of the velocity vector equals the square root of the squares. So now plugging that all in, this all ties into the fact that we are considering this all to be kinetic energy. Okay, so if we want to find the mean velocity of this, there's a couple other steps, but the whole point is at the end, the famous result of this is that from these arguments, tying the energy to kinetic energy, using the momentum partition function, and then normalizing it to get these exact coefficients to make it all normalized statistics, the mean velocity is, you find that, or let's call it a v, some scalar v, let's just call it that. The way you find that is you say, what is the integral of 0 to infinity of this scalar times this probability function integrated over all these? And by doing that, you get this magic, super famous, useful, powerful result that we're going to start maybe the next analysis on, is that the mean velocity of this distribution depends on the mass of the molecules you're talking about, and it depends on the temperature, basically. So the velocities pretty much depend on temperature, or to look at it the other way, the temperature is a measure of the kinetic energy of your systems. That's what one basis of temperature is. It's basically tying back to the energy of your system, specifically what? The kinetic energy in the translational motion. So this whole thing is the basis of temperature. One definition of temperature this is this is the basis of collision theory. So one way to begin to describe how chemical reactions happens is, in order for a chemical reaction to happen, they have to see each other. How do they see each other? They have to collide. How fast do they collide? It depends on how fast they're moving. How fast are they moving? Well, here's the mean velocity according to these arguments of this Maxwell velocity distribution. That's chemistry. When we're asking about momentum and viscosity, well, how can this momentum be transferred across these planes? Well, when they're moving across each other, they're going to collide. How do they collide? You can use their mean velocity of the Maxwell distribution. Same thing with mass transfer. Diffusion behavior is when you have a pocket of some component, one atom and molecule that's collected here that doesn't exist there. The natural behavior that's been observed is that it spreads out in space, and it goes toward from high concentration to low concentration naturally. How does that happen? It happens because these are always colliding with each other, and over time, those collisions result in a net transport, a net flux over space, over time. How fast does that happen? It depends on how fast they collide. How fast do they collide? Depends on the velocity that they're going. You can use this mean velocity of the distribution. And so that is mass transfer, heat transfer you can imagine as well, momentum transfer, viscosity, you can use this for gases, chemical kinetics, how fast does a chemical reaction happens. The speed of a chemical reaction cannot happen faster than they can see each other. So the fastest rate that any chemical reaction can happen is limited by how fast they can collide with each other. And a rough estimate, like I said, this is all idealized. There's more details to this, but you can use the fact that applying these assumptions, they have this mean speed. One way to understand where the speed comes from is from their mean velocity. So that's how the ideal gas equation came about. What it was saying is that you can assign so if you're going in the X, Y, and Z, I forget which one's the proper way. Maybe this is like X, Y, and Z. This has, in this direction, the energy of the X equals 1/2 kT. 1/2 kT, 1/2 kT. So the kinetic energy, the energy of the translational equals 3/2 kT because you have three different directions. And so if that's the case, you can see that that's how, and it depends on how many molecules you have, kBT. But after some other arguments, you can basically relate this to the other laws. And what happens is you can get some equation like this, the ideal gas law. So this is the energy, the amount of energy in the whole system is the number of molecules. This is the Boltzmann's constant, this is the temperature. So the number of energy in your system is proportional to the number of molecules, of course, but then this pressure times the volume relationship is also a way to quantify that. So this whole argument of energy be relating to temperature and the velocities, kinetic energy, is where the ideal gas equation came from. Okay, so it was a little abstract, but I hope it gave you a little bit of idea of this whole concept of how things developed the last 200 years was that before even atoms and molecules were decided upon and how they were accepted as the standard theory of how mass behaves, how we are all looking at this behavior. Maxwell and Boltzmann, they went with that idea. They said that in a gas, these atoms and molecules are shooting at each other, colliding sometimes, and the velocity, the energy you can attribute to this set ensemble of atoms and molecules can be attributed to potential energy, ignoring potential energy, tying it to kinetic energy, given to this specific shape. This function looks like this, and fitting it in with the other theories of quantum mechanics, it's been expressed in terms of this partition function based on momentum. And then if you normalize this to get integrate this whole thing to get 100% probability of something happening, you'll get these coefficients. And then you take the speed to convert this velocity into a scalar. And then you take the mean of that distribution. This is what you get. And you can also write this in terms of two molecule systems. So the mean velocity of A and B, two different molecules, equals, so the that's related to the mean of both. And should get something similar. So that's for a two-body system, or two different molecules in the thing, where this is their relative velocity. So we're going to use this. So we're going to use collision theory to find how things collide, because that can give us an idea of how things diffuse. It's a measure of mass transfer. So the natural tendency is for things that are concentrated in space, just because of, it's called Brownian motion. They're always colliding with each other. Einstein was the one who formalized, took this to the next step, and to develop this concept of diffusion, just by collisions, not by any pressure gradient, not by any draft or jet going from left to right. It's just anything in space is bouncing off of each other, and that results in some net motion from high concentration to low concentration. Okay, so that's all I had today. See you next time.